The next notion of interest that we'll discuss is that of state space partitions. We start with a state space that we called or denoted M. And then there is some induced dynamics on M. It could be by a trajectory of a continuous time vector field or a map T. But in any case, the dynamics itself creates subsets of M that might be of interest. For example, one such subset is an orbit. So it's the set of all the points that the trajectory reaches in backwards and forwards time. And one can start thinking about partitions of the state space. And the simplest one that one can think of is precisely the partition into orbits. So a partition is a splitting of the set M into subsets, such that the union of those subsets is M itself, and they don't intersect. So they're disjoint sets. So if you think about individual orbits in a system that has existence and uniqueness of solutions, they are separate. Orbits are separate as sets, so they're disjoint, and their union is the whole set M. So they constitute a partition, but the partition into orbits might not be always a good one to consider. So for example, consider the situation when M itself is the unit circle, the circle of radius 1 that we usually denote by S1. And the dynamics on it is the one that I've talked about before, which is just a translation along the circle by some omega. And so in the case when this omega is in particular omega divided by 2 pi, the whole circle S1 is parametrized by the angle theta that goes between 0 and 2 pi. And so when omega is rationally related to 2 pi, so for example, omega is 2 pi n over m, then we will start from some initial condition, jump around with omega, and come back to this initial condition after, let's say, m steps. But when omega is not equal to 2 pi n over m for any n and m integers, so note when omega is rational, n and m are some integers. But when omega is not 2 pi n over m for any integers n and m, then it turns out that the orbit itself is a dense set of points on this unit circle. And so what that means is that for any interval that you pick, and for any orbit that you pick, start from an orbit that has this as an initial, as a point on it, or here, and jump around, there is going to be a point of that orbit inside this interval, no matter how small the interval is. So in other words, every orbit of such a map, when omega over 2 pi is irrational, is going to be dense inside that circle. And so it's difficult to see how we exactly separate orbits because within each interval, there is a point of every orbit that the dynamics produces. Another example that's a even more complicated dynamically is that of the well-known chaotic map where the next iterate is twice the initial condition. So the next point that the mapping lands is twice the initial condition, but taken mod 1. So I can again draw this in the following sense. So the dynamics takes place on interval 0, 1. And this being 1/2. And now we're gonna draw the top here, and then this. So for any initial condition x, the map takes it to 2x. And then from that point, of course, we bounce off the y is equal to x curve and go to the next point, or rather bounce off the map, go to the diagonal, bounce off the map, go to the diagonal, and bounce off the map again, and so on. And it's well known that this dynamics, so the points where we land are here, 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 is chaotic on the interval 0, 1. In other words, with probability 1, the trajectories are again going to be dense, but they have another property, that of sensitivity to initial conditions. So if you take two trajectories that are very close by, for a while they might be kind of bouncing together and filling the points on the interval 0, 1. But there is going to be a point in time where they're going to separate, in the sense that one of them is going to stay, let's say, in interval 0 to 1/2, and the other one is going to land in 1/2 to 1. And one starts getting exponential divergence of trajectories that start very, very close together. This is called sensitive dependence on initial conditions, and we'll discuss it a little bit later in the context of asymptotic, what kind of asymptotic dynamics dynamical systems can have. So while this map has also an infinite set of periodic orbits that are all unstable, so for example, starting from any rational number, one actually gets a periodic orbit. But if you start very, very close to that periodic orbit, the trajectory will run away from the periodic orbit, and will do that ultimately exponentially. So this is a map that has the properties of chaos. As I said, we're going to discuss them just a little bit further down. But in some sense, it's the orbits themselves are again so complicated that even thinking about individual orbits over very long time might not make much sense. And in that case, in a very coarse-grained way, we can say, well, almost every orbit is going to fill the interval 0 to 1 densely again, and the dynamics itself is chaotic. So this interval 0, 1 and the distribution on that interval is the kind of thing that we might be interested in. So what can be made the case for is trying to understand whether there is any partition of the state space that somehow perhaps aggregates orbits that makes dynamical sense, that is induced by the dynamics itself. And that turns out to be an interesting concept to consider. And interestingly, it's closely connected to the aspects of operator theoretic analysis. So once again, a partition of the state space is a family of sets whose union is the whole state space, and then their intersection is zero, an empty set. And the partition of the state space into orbits is actually an example of an invariant partition. The general definition of an invariant partition is if we have a map T and we have some partition that contains some sets A, that contains some sets A, maybe indexed by some index alpha. And so for every such set A in it, we need to have that the inverse of the map takes that set into another set in the same partition. So to draw again a little pictorial version of this, there we have some sets that combine together or taken a union of give us the whole set M. And the idea of an invariant partition would be the one where if we would take a set A, then it would be true that that set A was mapped into, so all the points that map into A came from another set in that partition. It could be as simple as just splitting the state space into two portions, A and B, and let's say we find a splitting within which all the points in A get mapped to B by map T, and then all points in B get mapped to A. And in that case, you'll just be kind of flipping between the subset A and subset B. And this should convince us that finding some partitions would be a useful thing, because we would certainly like to know whether there are some collectives of initial conditions that get mapped into each other as the dynamics proceeds. So there is an example from what we've already studied a little bit, and that's this type of system that's called the Hamiltonian system. Let's say in 2 dimensions. So we have a function h, and then x dot is partial h with respect to y, and then y dot is minus partial h with respect to x. These systems arise from mechanics in which x would be a position and y would be a momentum. And in the case of such a system, so this is a frictionless mechanical system that has 1 degree of freedom, h dot is equal to 0. And what this means, so the Hamiltonian self is preserved. Remember, Hamiltonian in this case is the energy of the system. So the energy is preserved. And then let's consider the level sets of the Hamiltonian H, defined by, H or Hamiltonian or energy acquiring some constant value C. Clearly, they must be invariant, because this equation here says that that value C that we might have at some initial condition doesn't change over time. So H dot is equal to 0. This we know from mechanics, from previous classes. But here is an interesting point. H dot itself, the change of the Hamiltonian, is F, our vector field, that's the right-hand side of this, dotted with grad H. So it's the change of H in direction of the vector field. If we write this out, of course, because of the skew symmetry, that's precisely 0. But previously, we have defined eigenfunctions of the Koopman operator associated with this system as those functions that satisfy F. Again, I'm underlining if something is boldface in the notes. f dotted with grad phi is equal to lambda phi. If I found a function phi that satisfied this equation, then lambda would be an eigenvalue and phi would be an eigenfunction for the Koopman generator and therefore for the Koopman operator. So remember that this thing here is equal to A phi, where A is the generator that we have discussed. And so this calculation here really means that H dot, which is F dot grad H, consider this, being 0 just means that H itself is an eigenfunction of the Koopman operator of this system associated with eigenvalue 0. And so that's quite an interesting point, because of course the Hamiltonian, the energy of the system, is a very, very important physical quantity. And finding with this, different operator theoretic formalism, that it's a very important quantity in that formalism as well. Namely, it's one of the eigenfunctions. And eigenfunctions, as we argued before, are quite important as objects, as operator theoretic, spectral operator theoretic objects. So we found that the energy of the system, of a Hamiltonian system, or the Hamiltonian itself, which is the energy, is actually an eigenfunction, eigenspace 0 of the Koopman operator. And so that leads you almost immediately to the notion that, well, if one can find such a physical meaning in an eigenfunction at eigenvalue 0, how about all these other eigenfunctions? What is the physical meaning of some of the other ones that we can find? And that's a very fruitful study, as we are going to see, and one of the major themes in these lectures, namely the level sets of the eigenfunctions of the Koopman operator provide us with geometric and therefore physical information about the system that we're studying. So we talked about invariant partitions, and we could call the partitions that are of the type provided by the Hamiltonian, let's say, fixed partitions. Why is that? Because this level set, H is equal to C, the mapping takes that set, H is equal to C, into itself. So for, let's say, the harmonic oscillator, whose the level sets of energy are ellipses, the flow itself maps each orbit into itself. So it clearly satisfies this equation pretty much trivially with any set A in the partition being mapped in itself. You're taking inverse time for certain measure theoretic reasons that I'll discuss just a little bit later as we study measure preserving systems. But we could ask, well, there are other interesting partitions where the sets get mapped into each other and not just into itself. And the simplest of such non-trivial ones are periodic partitions. So if one takes a map T, a partition would be periodic with period n, provided that is invariant, and every set A in it satisfies T to the minus NA is equal to A for some integer n. Now, typically we take the smallest such integer n to reflect the exact periodicity. So here is an interesting non-trivial example in which a periodic partition arises. Remember the map x prime is 2x. Well, here we are going to consider the map x prime is minus 2x, where this map is again taken mod minus 1, 1. What that means is if the mapping takes the dynamics outside of the interval minus 1, 1, it is promptly returned to that interval. So for example, if starting from this point, we take, starting from this point, take minus 2x, go over here, right? Since this is bigger than 0.5, let's say it's 0.6, it will go to minus 1.2. But mod minus 1, 1 means we are going to actually consider it inside the interval, so we would put it at minus 0.2. And so how does the dynamics proceed? Here are the lines with a slope minus 2x. So in order to understand the dynamics, we can start, let's say, from this point. This is the diagonal. So we say, okay, from this point, minus 2x would be this. Bounce it off the diagonal to see where we get. So let's say this is around 0.4. We go to 0.8, take it to the minus, that will be minus 0.8. Then we proceed, bounce off this line here, go to diagonal, down, bounce off the line, go to diagonal, up, and so on. And so here are some interesting things to notice. If we start from interval 0, 1, then in the next step, we are going to land in the interval minus 1, 0. And then in the next step, we're going to land in interval 0, 1, and so forth. So in each step, we're going to flip from interval 0, 1 to minus 1, 0, and vice versa. But at the same time, if you take the second iterate of this, so you start somewhere here, you land here, and then you go back over here, the map, the dynamical system is x double prime is 4x mod 1. Now that's a chaotic map of the pretty much same type, but a little bit faster exponential divergence than x prime is 2x, and I've just described that other map. So that's going to have a, with probability 1, if you start from some point, we're going to have some random distribution of points on interval 0, 1. So it's chaotic. On the other hand, we found a pretty strong regularity when we consider the bulk property, which is anytime you start from 0, interval 0, 1, you go to minus 1, 0. So this map that we considered has an interesting partition, a periodic partition. Anytime I start in minus 1, 0, I go to 0, 1. Anytime I start in 0, 1, I go to minus 1, 0. And then, of course, 0 itself stays put. So the period is 2. Every 2 steps, everything returns to where it was, not exactly to the exact initial condition, but to the same interval in this partition it started from. And so we discovered a periodic partition in a system that is asymptotically over a long time going to have chaotic properties. And it does turn out that minus 1, 0 and 0, 1 are in fact level sets of a Koopman eigenfunction. In fact, it's a pretty easy one to figure out. Consider a function that is just of value 1 here, and then it has value minus 1 over here. Let me move this for a second. So the function that I'm considering, oops. The function that I'm considering has value one on this side, and then it has value minus 1 on this side. So if you took a look at any individual trajectory, and asked just the following question: is the trajectory in the interval 0, 1 or interval -1, 0? The answer would be, the sequence of answers would be -1, 1, -1, 1, -1, 1. So very, very ordered. And yet I argued that the dynamics of the system is chaotic. So the moral of the story is that you can have periodic partitions in systems that in fact exhibit chaotic dynamics, and they can be revealed to us if we compute the associated Koopman eigenfunctions. Now, another periodic partition, and quite an important example of one, arises in this continuous time system. R dot is 0, theta dot is omega. So R and theta are polar coordinates. And so clearly, again, the trajectories of this system are, in this case, circles where R, since R dot is 0, R stays constant over time. And theta dot is equal to omega, so theta just spins around clockwise. And so clearly we immediately identify one partition, that's partition into orbits. So each of these orbits is an invariant set, and partition into such invariant sets is a periodic partition. But there is another interesting one, and that's the partition into constant theta rays. So theta is equal to constant, right? Why is that an interesting partition? Well, if you start from any of these theta is equal to constant lines, at some time t or tau, you're going to reach another one of those lines. So all the initial conditions that start here are going to come to another one of those lines at equal time, because the solution, the flow, starting from R0 theta 0 is R0 theta 0 plus omega t. So it doesn't matter which R0 you start from. If you start from the same theta 0, you're going to reach the same theta in the same time. And in particular, after a time capital T, you're going to come back to the initial rate. Right? So clearly, this is a periodic partition where the periodicity of the partition in the continuous time is defined by requiring that for any set A in the partition, those sets A would now be these rays, there needs to exist, there is a number tau, which is the time at which A returns to itself, or rather the mapping in inverse time of A is A itself. So if you start from here and go back in time, you'll come back. And I notice now I have argued that theta is in the clockwise direction, but then I've reversed the direction of time here. Hopefully that didn't introduce a confusion that is too large. Okay, so the partition into rays here is a periodic partition. Partition into constant R is an invariant partition. In fact, a fixed partition. Every set is mapped into itself, and so those two partitions are, one would argue, physically important. R is equal to constant corresponds, for example, for the harmonic oscillator to constant energy, and theta is equal to constant corresponds to constant phase. So both are physically quite important, and that's the set of ideas that pertains to these partitions of state space. As I mentioned, we are going to continue and discover quite a bit more along these lines. And a big theme is the discovery of the geometrical properties of dynamical systems using the partitions that are induced or generated somehow as level sets of the associated Koopman eigenfunction.